Hi everyone. Today we are studying Laplace transformations. So first of all, see what is the integral transform. So let us suppose we are having k of s comma t, a function in s and t, where s is independent of t, and we are supposed to find the integral transform of the function f of t. So the integral transform will be denoted by f of s, and it is equal to integral minus infinity to infinity k of s comma t f of t dt. Okay, so the integral transform which we will get will be in the terms of s, and k of s comma t, this function is called the kernel of the transformation. Now when we will change this kernel to to say k of s comma t is equal to 0 when t is less than 0, and is equal to e raised to minus st when t is greater than or equal to 0. Then the transformation f of s will be of the form integral 0 to minus infinity to 0, 0 f of t dt plus integral 0 to infinity e raised to minus st f of t dt, right? And this will be equal to integral 0 to infinity e raised to minus st f of t dt itself, because the first term of the integral will be obviously 0, and then we say f of s, it is also denoted by L of f of t, that is the Laplace transformation of f of t is integral 0 to infinity e raised to minus st f of t dt, and this is called the Laplace transformation of f of t. All right, now we will see the Laplace transformation of some basic functions. So for that, first of all, let us assume that the function f of t which is given to us is 1. Okay, then the Laplace transformation of 1 will be equal to integral 0 to infinity e raised to minus st into 1 dt, and this is equal to e raised to minus st by minus s integral 0 to infinity, and this is equal to 1 by s. All right, when you will put the limits, you will see it is equal to 1 by s. So therefore the Laplace transformation of 1 is 1 by s. Now let us assume that the function f of t which is given to us is t. Okay, now f of t is t, then what is the Laplace transformation of t? It is again given by integral 0 to infinity e raised to minus st into t dt. Okay, so now we will use eyelet, and t will be the first function, e raised to minus st will be the second function. So this is equal to first function into integration of second function minus whole integral derivative of first function, that is 1, into integration of second function dt, and the limits will be from 0 to infinity, and this will be equal to t by minus s e raised to minus e raised to st plus st minus minus plus 1 by s square, sorry, 1 by s. Now integral of e raised to minus st will be e raised to minus st by minus s, and the limits are from 0 to infinity. So this is what we have. So we have, now moving ahead, I can take minus 1 by s common, and then I have to evaluate the limit of t by e raised to st from 0 to infinity, and minus 1 by s square can be taken common, and then I have to evaluate the limit of 1 by e raised to st itself from 0 to infinity. Now minus 1 by s. Now as t tends to infinity, the numerator t is tending towards infinity, and e raised to st, the denominator is also tending towards infinity. So we are getting infinity by infinity form. We can apply L'Hopital rule, and therefore we have to evaluate the limit of 1 by e raised to st into s. Now, as t tends to infinity, we know e raised to st is tending towards infinity. So the whole term is tending towards 0. So 0 minus. Now, as t tends to 0, numerator is tending towards 0. And what about denominator e raised to st? It is tending towards 1. So this is equal to 0 by 1, that is 0. So this is giving us 0. Now minus 1 by s square. Now 1 by e raised to st. S this. We have to evaluate the limit of this. So we are having minus 1 by s square. As t tends to infinity, e raised to st is also tending towards infinity, and therefore 1 by e raised to st is tending towards 0. So we are having 0 minus. Now as t tends to 0, e raised to st is tending towards 1. So 1 by e raised to st is tending towards 1, and therefore we have 1 here. And hence the answer is 1 by s square. So what are we getting? We are getting that the Laplace transformation of t is 1 by s square. Similarly, you can evaluate the Laplace transformation of t square, and you will get that the answer is 2 by s cube. When you will evaluate the Laplace transformation of t cube, you will get this as 6 by s raised to 4, and 6 can be expressed as 3 into 2 by s raised to 4. I can even multiply 1. So this is giving me 3 factorial by s raised to 4. Here, therefore, in general, I can say that Laplace transformation of t raised to any n will be equal to n factorial by s raised to n plus 1. Alright, so this is the Laplace transformation of t raised to n. Now, let us assume we are finding the Laplace transformation of, say, some e raised to at. We are given a function f of t as e raised to at, and now we are finding the Laplace transformation of it. So Laplace transformation of e raised to at will be equal to integral 0 to infinity e raised to at into e raised to minus st dt, and this is equal to integral 0 to infinity e raised to a minus s into t dt, and this is equal to e raised to a minus s into t by a minus s. And now we have to evaluate the limit from 0 to infinity. So now to evaluate the limit, as t tends to infinity, e raised to a minus s t will be tending towards 0, as we have s is greater than a. Because s is greater than a, we will be having e raised to a minus s t is tending towards 0. So the first term will be giving us 0 minus. Now as t tends to 0, it is obvious that e raised to a minus s t will tend towards 1, and therefore we will have 1 as the next term. So we will have minus 1 by a minus s, or we can have 1 by s minus a. So therefore the Laplace transformation of e raised to at will be equal to 1 by s minus a. Alright, so this is what the Laplace transformation of e raised to at is. Now, similarly, on evaluating, we can see that the Laplace transformation of sine at will be a by s square plus a square. Laplace transformation of cos at will be equal to s by s square plus a square. Laplace transformation of sine hyperbolic at will be equal to a by s square minus a square, and Laplace transformation of cos hyperbolic at will be equal to s by s square minus a square. Now, to evaluate the Laplace transformation of sine hyperbolic at, we can remember simply that sine h at will be equal to e raised to at minus e raised to minus at by 2, and cos h at will be equal to e raised to at plus e raised to minus at by 2. All right, and we can evaluate the Laplace transformation then. So these are the Laplace transformation of few known functions. If you want if you want me to find the Laplace transformations of these functions, you can let me know. I will solve them for you. And now, one major thing to remember or to note down is that if we are given a function f of t, then we have that the Laplace transformation of that function f of t is, say, some f of s. All right. So if this is happening, in that particular case, we even have the Laplace inverse of the function f of s. And the Laplace inverse of the function f of s will be nothing but f of t. All right. So this is the thing we have. And therefore, now I told you, now we found that the Laplace transformation of 1 was 1 by s. So from this I can say that the Laplace inverse of 1 by s is 1. We found that Laplace transformation of t is 1 by s square. So I can say that Laplace inverse of 1 by s square is t. And in general, we noted that Laplace transformation of t raised to n is n factorial by s raised to n plus 1. So this gives us that Laplace inverse of n factorial by s raised to n plus 1 is t raised to n. All right. And before this, yes, one thing which I forgot to mention is that suppose we are finding the Laplace transformation of the function af of t plus bg of t. This is the function of which Laplace transformation we are finding. So this is equal to the Laplace transformation of a into L of f of t plus b into L of g of t. Here a and b are constants, and f of t and g of t are functions in t. All right. So because of this linearity, this is showcasing that the Laplace transformation holds the property of linearity. And by this property, this particular thing now can be expressed as basically or from this particular L of t raised to n is equal to n factorial by s raised to n plus 1. I have that 1 by n factorial L of t raised to n is 1 by s raised to n plus 1, or basically this is giving me L of t raised to n by n factorial is 1 by s raised to n plus 1. So therefore, now I can say that the Laplace inverse of 1 by s raised to n plus 1 is t raised to n by n factorial. All right. So either I can say this, or I can say that Laplace inverse of n factorial by s raised to n plus 1 is t raised to n. Both are equivalent. So this was about the about finding the basic uh, Laplace transformation of sine at is a by s square plus a square. So this gives us that Laplace inverse of 1 by s square plus a square is equal to 1 by a sine at. And similarly, we can find the Laplace inverse of s by s square plus a square, and that will be equal to cos 80. So therefore we have Laplace inverse of 1 by s raised to n plus 1 is equal to t raised to n by n factorial. Similarly, we can find the Laplace inverse of all the other functions. And now let us do one problem. So the question is to find the Laplace transformation of sin t cos t. So now we don't know actually what is the Laplace transformation of sin t cos t directly, because it is not similar to any of the functions of which Laplace transformations we have found out. So now we can use a trigonometric identity that 2 sin t cos t is equal to sin 2t. And by that, if we multiply and divide by 2, we have this function same as sin 2t by 2. And now we can find the Laplace transformation of sin 2t by 2. So this is obviously 1 by 2 into Laplace transformation of sin 2t. And this is equal to, now Laplace transformation of sin at is a by s square plus a square. So therefore here sa is 2, it will be 2 by s square plus 2 square. 2 gets cancelled and therefore we have 1 by s square plus 4. This will be the Laplace transformation. Alright, and another question which we can do is to find the Laplace inverse of 6 by 2s minus 3. Okay, so we have to find the Laplace inverse of this particular function. So first of all, remember that the transformations, Laplace transformation which we have found till now, all of them had the coefficient of s or s square as 1. All right. So first of all, consider this 6 by 2s minus 3. Now, first of all, let us make the denominator of s as 1. So the coefficient of s is 1. So we can take 2 common and we are left with s by s minus 3 by 2. And this is equal to 3 by s minus 3 by 2. So Laplace inverse of 3 by s minus 3 by 2 will be equal to, now 3 Laplace inverse of 1 by s minus 3 by 2. So observe that the thing inside the bracket is of the form 1 by s minus a. And do you know of which function the Laplace transformation is equal to s minus a? So obviously function is e raised to at. So therefore we will have 3 into e raised to 3 by 2 t. So therefore we have Laplace inverse of 6 by 2s minus 3 is equal to 3 e raised to 3 by 2t. So this is the way to find the Laplace transformations and the Laplace inverse. Similarly, we can do one more question, and in this we can find the Laplace inverse of 3 plus 4s by 9s square minus 16. So for this can be expressed as 3 by Laplace inverse of 3 by 9s square minus 16 plus Laplace inverse of 4s by 9s square minus 16. We know the linearity holds. So therefore now this is equal to Laplace inverse of 3 by, again let us make the denominator of the coefficient of s square 1. So we can take 9 common and we are left with s square minus 16 by 9 plus Laplace inverse of 4s by Again, we can take 9 common, s square minus 16 by 9. This is what we are left with. So we have L inverse of, now 3 by 9 we are having, so 1 by 3 we can write into 1 by s square minus 16 by 9 plus L inverse of, this is 4 by 9. Okay, we are having 4s by 9, or I can just keep 4 by 9 here, and this is multiplied by s square minus 16 by 9. So this gives me, this is equal to 1 by 3 times Laplace inverse of 1 by s square minus 6 by 9, 16 by 9 can be expressed as 4 by 3 whole square, plus L inverse of 4 by 9 again can be taken out. I'm left with s by s square minus 4 by 3 whole square. This is what I have. So we know that the Laplace transformation of sine h at is a by s square minus a square, and this gives me that Laplace inverse of a by s square minus a square is sine h at. And if I want to take this a out, or I just want to have 1 here, then a will come here in the denominator of the right hand side. So this is what we have. And similarly, I know that Laplace transformation of cos h at will be s by s square minus a square. It is better to learn all these Laplace transformation and the inverse also. So this will be equal to cos h at. Now I can use both of these to proceed ahead. All right. So now this will be equal to, so the Laplace inverse of the function was 3 plus 4s by 9s square minus 16 is equal to, from here we are having 1 by 3 Laplace inverse of 1 by s square minus a square. So this will be sine h 4 by 3 t by a, which is same as 4 by 3, plus 4 by 9. Now this is cos h, a is 3 by, sorry, 4 by 3 t. So therefore, as a result, we have 4 sine h 4 by 3 t, or sorry, 1 by 4. Yes, here we will be having 1 by 4. So 1 by 4 sine h 4 by 3 t plus 4 by 9 cos h 4 by 3 t. Alright, so this is the Laplace inverse of 3 plus 4s by 9s square minus 16. Okay, now the next thing which we will be looking is some properties. So the first property is shifting property. So what the shifting property says? So the shifting property says that Laplace transformation of any function of the form e raised to at f of t, okay, this will be equal to f of s minus a. It basically says that if we have a function f of t and it is multiplied by e raised to at, we have to find the Laplace transformation of e raised to at f of t. Then this will be equal to nothing but the Laplace transformation of f of t, L of f of t, and this will be say f of s, and then just replace s by s minus a. S should be replaced by s minus a, and this will give us the Laplace transformation of e raised to at f of t. So for an example, let us suppose we are finding the Laplace transformation of, say, e raised to minus 3t t cube. Okay, so observe this. Compare e raised to 80 f of t with e raised to minus 3t t cube. So here f of t is t cube, e raised to 80 is e raised to minus 3t, and therefore a is same as minus 3. These are the things we have. And now this is equal to f of s minus a, and f of s minus, to find f of s minus a, first of all find f of s, that is nothing but L of t cube, and we know that L of t raised to n is n factorial by t raised to n plus 1. So this is equal to 3 factorial by t raised to 4. All right, sorry, s raised to 4. Here also we will be having s. So we are having s raised to 4 here. Now f of s minus a, that is f of s minus minus 3, is f of s plus 3, and this is equal to 3 factorial by s plus 3 whole raised to 4. So this is the answer of our question. The Laplace transformation of e raised to minus 3t t cube will be equal to 3 factorial by s plus 3 whole raised to 4. So these are few properties using which the work becomes easier and we can find the Laplace transformation easily. So let us see the next property. Now the next property says that uh, if we are multiplying a function y by t raised to n, then how we can find the Laplace transformation easily. So for this property says that L of t raised to n f of t is equal to minus 1 raised to n d raised to n by ds raised to n f of s. All right. So this is saying that suppose you are finding the Laplace transformation of a function t raised to n f of t. A function is of the type t raised to n f of t, and you know the Laplace transformation of f of t, then by this formula you can find the Laplace transformation of the function. So again, let us take the same example. The example which we took earlier was to find the Laplace transformation of L t cube e raised to minus 3t, right? This is the example we took now. L e raised to minus 3t t cube or t cube e raised to minus 3t. Both are same. So by both of these methods, we can find the Laplace transformation. So now this is same here. If we compare, f of t is e raised to minus 3t, right? And n is 3. So the Laplace transformation will be equal to minus 1 raised to 3 d cube by ds cube of f of s. So f of t is e raised to minus 3t, and therefore f of s will be 1 by s plus 3. So d cube by ds cube of 1 by s plus 3. Now you can find the answer, and the answer will give us nothing but 6 by s plus 3 whole raised to 4. All right, and you can see this is same as the answer we found in by the previous method. 6 is nothing but 3 factorial. So we got the same answer by both the methods. So you can use either of the method and you will get the same answer. So when first property was shifting property, second property is multiplication by t raised to n. Now we can look at few more other properties, and this property is regarding derivatives. Okay, so what does this say? Suppose f of t is a function whose Laplace transformation is f of s. This you know. Now You are finding Laplace transformation of f dash of t. So is there any formula using which you can find this? So the answer is yes. This Laplace transformation will be equal to S L of f of t minus f of 0. Alright. So Laplace transformation of derivative of f is equal to S times Laplace transformation of the function f of t minus f of 0. Now, if you are finding the Laplace transformation of the derivative, it will be equal to S square L of f of t minus S f of 0 minus f dash of 0. Okay, so the Laplace transformation of f double dash of t is given by this. Now I will also tell you the Laplace transformation of f triple dash of t, that is the third derivative of f. This will be equal to s cube L of f of t minus s square f of 0 minus s f dash of 0 minus f double dash of 0. So this is the formula using which you can find the Laplace transformation of the derivatives of the function f of t, provided you know the Laplace transformation of the function. So here there will be no need of doing the finding the derivatives again and again of the function and then proceeding ahead. You can simply use these formulas. So in general, Laplace transformation of fn of t will be equal to s raised to n. Observe here we are having third derivative, the power of s was 3. So here nth derivative s raised to n L of f of t minus s raised to n minus 1 f of 0 minus s raised to n minus 2 f dash of 0 minus moving on like this n minus 1th derivative and putting t is 0. So this is the formula by which we can find the values of the higher derivatives. Alright. Now after this we have the case of integrals. So when we are dealing with integrals, what happens in that particular case? So when we are dealing with integrals, suppose f of t is a function of whose linear transformation is L of f of t or f of s. And now you are finding in the Laplace transformation of integral 0 to t f of t dt. This is equal to 1 by s L of f of t. Simple. Okay. So the Laplace transformation of the function will be equal to this. So suppose, for example, uh, you have to find the Laplace transformation of integral 0 to t, say sine at dt. This is the function of whose Laplace transformation you have to find. So obviously here we can see f of t is sine at, and I know that the Laplace transformation of sine at is a by s square plus a square, and therefore the answer will be 1 by s into a by s square plus a square. Alright, so this is the Laplace transformation. Similarly, suppose we have to find the Laplace transformation of integral 0 to t sine t cos t dt. So we have f of t as sine t cos t, and we have already seen in the previous examples that the Laplace transformation of this function is equal to 1 by s square minus 4. Okay, so the Laplace transformation of this function is 1 by s square minus 4. So therefore the Laplace transformation of integral will be 1 by s into 1 by s square plus 4, that is 1 by s into s square plus 4. So this gives the Laplace transformation. So this is an easy method to find the Laplace transformation of the functions. Okay, so that's all for today. Thank you. And if you have any questions, you can put them down in the comment. I will solve them for you. Thank you.